This is Dr. Harris, and I'm going to go over some of the material that we missed this past week when I was out sick. So we're looking at Chapter 7, and we're discussing memory elements. I'm going to supplement our lecture with slides from another text, as I believe it goes into some of the details of these things a little better. So I'm going to start with that, actually. So let's look at an example of like a real-world problem. If we are on an airplane, we have the button that can call the flight attendant sitting right above our heads. And we push the call button and we release it, and a light comes on. As that happens, we can then have the flight attendant come over and push the cancel button, and they can attend to our needs if we wanted some more peanuts or whatever. So how would we build a digital logic circuit in which I can momentarily push this call button and let go of it, and it will still hold that light on? If we take a look at maybe this first attempt at this, we could say give some feedback from the output back to one of the inputs. Well, if we do that, we will get a call function where I push the button once if I make S a 1, and then I make S a 0 by moving my finger off the button. That will set a 1 on my output here, which feeds back in and will continually give me a 1, regardless of what S is at that point. The problem with this is that I could never cancel the button. I'd never be able to turn off the LED. So when the flight attendant comes over to hit the cancel button, the light will not go off. The cancel button doesn't exist. So there's a better way of doing that. And this way is called the SR Latch. And there's actually a couple of different ways to build SR latches. So let's take a look at this. Well, for one, what is an SR latch in general? So we have two inputs called set and reset, and we have two outputs called Q and Q naught. They are always the inverse of one another. And we also have the output of Q fed back into the input of one of our, in this case, a NOR gate. And then we have the output Q naught fed back into the other NOR gate. What this does is it allows for a pulse to be put on our S input. And I'm going to actually run this slide because it's animated. So if I assume that we have zeros on my input, we don't really know what exists over here on my output at any given moment, unless I've put data on there. So let's just say I don't know because I just turned the circuit on. So if I have a 0 for my S and a 0 for my R, these are known as the set and the reset pins. So if I give S a 1, even momentarily, what that does is that sets up a 0 on the output here, and that 0 gets fed back in to the input of this other NOR gate. And so if you have a NOR gate, any 1 on your output gives you a 0. And then if you have two zeros on your input, that gives you a 1. And so this 1 is then fed back in to the input of this gate, which sets up the condition for a 0 on the output again. And so basically this thing is constantly feeding itself the input that it needs to hold a 1 on the output. Even if my S value changes from a 1 to a 0, this still has this 1 being fed back into it, and therefore it will continue to hold this value on the output. Now, if I want to turn it off, if I want to turn my output to a 0, I pulse, or I put a 1 on my R input, or my reset. And what this does is it basically forces my output on this pin to be 0. And since this is 0 and my set is a 0, that forces this to be a 1, which then feeds back into the other one. So it's a continuing cycle, and it stores the value of 0 on my output Q. Now this is shown again in this particular slide. So if I have a 1 on my reset, for instance, and a 0 on my set, and here they're calling their output Q and T. And you can see that they've actually flipped which side was the set and reset from those other slides. It just depends on what the book you're using puts on the top here, whether it's set or reset. But let's imagine that we don't know what our outputs are at any given time before we set or reset. So we're just going to say that we're not sure what these values are for T and Q. But if I put a 1 on my reset, what happens? Well, if I look over here, this is a good reminder. If you look at the truth table of the NOR gate, a 1 NOR anything gives you a 0. And so that sets up a 0 on my Q, or my output. So a 1 on my reset sets a 0 on my output, which then feeds into my other NOR gate. And if, again, you look at the truth table, 0 NOR 0 gives you a 1. And so that's what happens in the second set of time. That 1 feeds back into over here, such that now I don't care what my R value is, because my other input is a 1. And it's going to sustain this 0 on the Q. And so now I've got R and S are both 0. However, my outputs, I know what those are. They are set right here to 0 for Q, and T, or otherwise known as Q naught, is a 1. And this gets sustained by that feedback that I was talking about. So now what happens if I hit the S button? If I make S equal 1? Well, if I do that, that forces my output of S to become a 0. And this 0 feeds back into the next NOR gate. And since it's a 0 on my R and a 0 here, that gives me a 1 on the output, which then feeds back into the NOR gate on top, sustaining that value. So my output Q changes to a 1. Now the biggest thing to note about this is, if I want my Q to be a 1, I put a 1 on my set. If I want my Q to be a 0, I put a 1 on my reset. If I've got zeros on both of these, then Q is going to retain whatever value it had in it before. So whatever the last command was, either set or reset, that's what it's going to do. It's going to either be a 1 or 0 based on that. Now, what happens if I happen to push a 1 on both of those? So this shows, go back to the call attendant, I can push the call button, that's fine. And then if I push the cancel button, that would cancel it. So that works. But what happens if I push the set and the reset at the same time? Well, I get this weird situation where the output oscillates between a 1 and a 0. And it will continue to do that forever until I change, turn the power off and whatnot. So you never want to have a 1-1 on the inputs of an SR latch. And so we can actually fix that by adding a little bit of circuitry here, so that I can never possibly get a 1 on my S and a 1 on my R. And so this shows one example of how to do that. We have an inverter connected to an AND gate here, and the cancel button is also attached to this AND gate, which goes to our R. So in effect, my R is always going to be the inverse of my S. Now, it only gets forwarded if the cancel button is pushed. So if I push the call button, this becomes a 1. So my set is a 1. That forces my R value to be a 0 because the input of this AND gate will be a 0. Then I've got a set here, so my output Q is a 1. The light comes on. Now, if I want to cancel it, I push the cancel button, so that gives me a 1 here, and I make sure the call button is not pushed, so that gives me a 0 here, which is inverted to a 1. So the input to this AND gate is 1, 1, and the output is then 1. And so that will turn my Q off. It will make it a 0. So that is the key points with a SR latch. You want to only activate one at a time. Now you can build an SR latch out of either NOR gates or NAND gates. And so this slide shows you how to set that up. So with NOR gates, you have normal active high inputs. So if I want to set my Q or make a 1 appear on my Q, I push a 1 on my set or my S input. However, if I build this out of NAND gates, then I have inverse logic or active low inputs. So if I want to set my Q, then I have to put a 0 on my S. And the natural state of both of these would be 1, 1, not 0, 0, where the natural state of this is 0, 0. That stores whatever's in Q. Here, it has to be 1, 1 to store whatever is in Q. So you can see they show in this particular slide, let me see if I can zoom in. Well, there we go. So if you look at this, you can see this is a NOR gate, this is a NAND gate. If I click here, well, this is also a NAND gate. This is just the De Morgan's version of a NAND gate. If you remember, you push the bubble through to come to the other side, and you change the type of gate it is. So if you ever see this in a book or in a schematic or a data sheet, don't be confused by it. It's just the De Morgan's of a NAND gate. So it does the exact same function. So once we've talked about the standard SR latches, how might we use these? Well, in this particular example, what we're looking at doing is we can force our output to be a nice clean 0 to 1 transition. And in this case, what we're doing is we have a switch that is going to select a ground, gets connected to either my S or my R on this particular latch. These resistors are constantly pulling the values of these S and R's pins to 5 volts. So, and notice that these have a bubble in front of the inputs. So this is a S naught and an R naught. So I can assume this is built out of NAND gates. And so what's happening here is these resistors are called pull-up resistors, and it's putting 5 volts or a digital 1 on the inputs at all times. And then this switch connects one of the 2 inputs to ground. Only one of them can be connected to ground. And so you flip the switch, it will go from set getting a 0 to reset getting a 0. And that will store whatever that value is, whether it's the set or whether it's the reset, in the output of the Q here. Now we can find these on some 7.4 LS chips that we have in the lab. And these usually have 4 sets of SR latches here. Now there's a variation on the SR latch called the gated SR latch. And this is one representation of it. Now remember, this is the De Morgan's of a NAND gate, so this is the inverse input. This is S naught here, so we have to have an inverter on this AND gate. But in this other book, it shows a very simple way of doing that. We just use the NOR version of the SR latch and regular AND gates. This will produce the exact same results. It's just a little easier to comprehend. So, looking at what a level-sensitive SR latch is we have S and R as inputs that we can, configure individually. We can do S as a 1 or R as a 1 or both of them as a 0. We don't want it to ever have the situation of S and R being both 1. We haven't added circuitry to fix that just yet, but in this particular case, what we're going to do is we only want to pay attention to these inputs whenever my enable pin here, or my clock pin, is a 1. So if this pin happens to be a 0, then that makes these AND gates basically output zeros. There's nothing that's going to happen, because anything AND 0 is a 0. However, if this is a 1, then our S or our R could be toggled to a 1, and it will then set up the appropriate function on our output Q and our Q naught. And so this is what it looks like on the inside, how to build it, and this is the typical schematic symbol for it. And we've got the same kind of thing here. You can see we've got just a block to show it in the schematic. Here we have the exact same thing, but if you would remember, two inverters cancel each other out. So this is an inverter here, an inverter there. If I take this inverter on this side and stick it over here, then that turns this into a NOR gate. Here that cancels with that one, and I take this inverter and put it over here, so that makes that a NOR gate. So this is exactly the same functionality as the other gated latch I just showed you. So it does the same thing. I can only forward the values of S and R to the actual SR latch if the enable is a 1, because otherwise you're trying to AND some value with a 0, and that's going to get you a 0. Now here comes the simplest latch that I can think of that is the easiest to configure. This is the D latch, which basically is a gated SR latch, but what we've done is we put an inverter here between our S and our R. So again, you can never get into that weird state where S and R are both 1s, because that does this weird oscillation thing forever. It's a nightmare. You don't know what the value is going to be on the output whenever you read it. So you never want to get in that situation. You wire it such that you can never have S and R equal the same thing. And so the way this works is whenever I put a 1 on my enable, whatever data is on my D pin gets forwarded to my output. So the rule is Q follows D when the enable is active. Another way to look at this is if I look at these other slides here, this is the same exact thing, except again we're using just AND gates and NOR gates instead. So it's a slightly different configuration, but the principle is the same. I've got the gated SR latch here, but this shows kind of the interior. So my D input is actually my S input on my gated latch, and my R input here is the inverse of S. So again, I could never get in a situation where I've got a 1 and a 1 on my S and my R. And this is the exact same function of the other one that we were just looking at from the other slides. So if I put a 1 on my D and then I put a 1 on my C, then this data gets clocked over to the output, or gets sent over to the output here. And so that's a standard D latch. And D latches are really easy to use because whatever you want to store, you just put on the input and hit the enable, and it automatically locks that in there. So here's the truth table. So if D is 0 and enable is 1, then my Q is a 0, and we call that the reset because we're resetting our output to 0. If I put a 1 on my D and my enable is a 1, we have a 1 on the output. That's called my set. Now, if the enable is 0, I don't care what my input is, because I'm just going to store that Q value over and over again until you change it for some reason using one of these other commands here. So the D latch just easily stores a single bit of data. Now, we can use the D latch, but the D latch has some faults. What if I want to store this data for a long period of time, but my input here is an oscillating signal on my enable or my clock? So, for instance, what if I have a bunch of D latches connected together like this, and I want to clock the inputs here, and for every time I oscillate one time, I want to put a bit of data here, and when it oscillates the clock, I shift over by 1. Oscillate the clock again, shift over by 1, and so forth. Well, with a D latch, I have an issue doing that, because as long as my clock is a 1, then it will propagate through. So how many nanoseconds does it take to process through the gates of this one, into the gates of this one, into the gates of this one, and then into the gates of this one? Depending on how long that takes, I might have a clock signal that's too long to just do one shift over for every clock cycle. I could try to fix that by having a shorter time when my clock is enabled, but that really isn't a good way to do it, because it can the processing time can change. So what we do is we actually build what's called a flip-flop. And a flip-flop is two latches connected together, and we connect an inverter on their enable pins. So here I have the CM and the CS. We've got the master and the servant. And this actually only sets the data on the output on the rising edge of this clock. Now, that might not make a lot of sense. What do you mean the rising edge of the clock? Well, if I have a 0 on my clock here, that gets inverted to a 1, and it enables this first latch to be on. And so if I put a 1 on my D, that can, since this D latch is enabled, that can process to the Q here in the middle. However, it can't go any further because I've got a 0 on my clock, right? So it'll stay here the entire time that the clock is low. As soon as the clock goes high, then that turns this latch off. It's no longer going to react to the input, and it turns this one on. And since I have a 1 stored right here, that 1 gets processed to the output. And so what I'm doing is only on that edge can data move from this side to this side. And we can see that in a multisim simulation as well. So if I have two D latches in this configuration with an inverter between the first and second latch, I can get, let me simulate this. It takes a second. But if I have these two latches, here is my first latch, here's my second latch. I have these probes set up so that you can watch the clock. These are red. And then I have these probes set up so that you can watch the data. These are blue. And so our actual input of the flip-flop is right here, and our output of the flip-flop is way over here. So if I say that my clock is a 1, this data goes nowhere because I'm inverting that 1 and turning this latch off. If I make that clock go to 0, what happens is I turn on this latch, so it forwards whatever this data is to the middle here. But it can't go any further than the middle because I've got a 0 on my clock turning this latch off. As soon as I go from a 0 to a 1, it sees the rising edge of the clock, in other words. What's going to happen is it turns this latch off and this one on, and that will forward this to the output. And so now, with this latch on and this one off, it doesn't matter what my input to the flip-flop is, because it's not going to go past this disabled D-latch. This is just storing the 1 from earlier, so it's actually not going to change. But the output changes on the rising edge. So notice I just made my clock a 0. Well, that didn't really do anything to my output of the flip-flop, did it? If I go from 0 to 1, now it's going to load whatever value is here on the output. And so we've got a 0 on the output. And so I could do this with the data to just prove to myself that that's how it works. Now, what happens if the inverter is connected to this latch instead of this one? So you could see the position of the inverter here. On the first one, the first circuit here, it goes to the first latch. On this circuit, it goes to the second latch. What this is called is a falling clock edge D-latch. So it is only going to forward data to the output when you have the falling edge of the clock, when the clock goes from a 1 to a 0. And this is proven by having a 1 on the clock right now. The first latch is enabled, and this 1 is traveling to the middle. As soon as I change this to 0, it's going to turn this latch off and turn this one on, because the inverter is inverting the clock to this one as a 1. And it's going to forward this data from this D input to the Q output. So let's watch that happen. Now I can change my input data on the first latch, but nothing is going to be forwarded to the output of the flip-flop or even to the output of that latch because it's not enabled. My clock is a 0. So if I want to forward this data here, this 0, to my output here, then I have to go from the 0 to the 1 to enable this chip. And now that's storing a 0 in the middle of the flip-flop. That doesn't get forwarded to the output until, again, I find the falling edge of my clock. And so you can watch how this actually propagates. The output only gets updated on the falling edge of the clock. And so you can see the difference there. Now that creates a flip-flop out of 2 latches and an inverter. And a flip-flop has a symbol, if I could zoom in here. Why is it not letting me zoom in? Okay, I'll go back to the presentation real quick. So a flip-flop has this symbol. It's got a little greater than sign. And what that means is it's looking for the edge of the signal. It doesn't care if it's a 0 or a 1 currently. It wants to see the transition from either a 0 to a 1, which is a positive edge, or this is a symbol for a negative edge triggered or falling edge triggered, where your input goes from a 1 to a 0. So just note that there's a little inverter in front of your clock input. And so flip-flops are very useful because now if I go back to this design and I want to clock data in one at a time and I want to know exactly how far I've clocked it, Well, I can use either one of these two clock inputs, whether my clock is nice and even like this, or whether I have a drastically skewed clock. It doesn't matter. I'm still going to get the same number of shifts from each one of these, because they're both rising clock edge on each one of these flip-flops. These are both clocks with two rising edges, and therefore I will be able to clock in my 1 here and then clock in a 1 to the next one. Again, compare that to the latch, where if I had a 1 last a longer period of time, then my input could go through a longer string of these latches, because the entire time that that latch is a 1, the data gets forwarded through. So now we have a clock edge triggered device. And again, here are the two symbols. This is a positive edge, rising edge trigger, and this is a negative edge or falling edge trigger. So you go from 1 to 0 there. Now let's look at, this is the slide. So what we've looked at so far is the basic element for memory storage, an SR latch. How do we build an SR latch into a level sensitive SR latch, which allows us to use the C here as an enable. Then we learned how to build that into a D latch, and then we learned how to build a D latch into a flip-flop. And we can actually make this a rising edge flip-flop. This is the configuration of a rising edge, or a falling edge flip-flop. The inverter goes instead to the second latch in the flip-flop to make it a falling edge. And so we can consider these as our memory elements. And these are the basic memory elements. Now I mentioned we have a D flip-flop and a D latch. This is the truth table for the D latch. So if the input on D is a 1, the clock rises, my output gets a 1. If I get a 0 on my input and the clock rises, I get a 0 on my output. Similarly, with the negative edge triggered or falling edge triggered, a 1 on my input waits for the clock to drop, then it stores on the output. Any other time, it is just storing that data. The Q will stay the same until the next time the clock falls on this negative edge trigger, for instance. So it's a very useful tool. Now we have another kind of flip-flop that's called the JK flip-flop, which is very, very similar to an SR latch. So we have two inputs instead of the one. So if I have, you can think of your J and your K kind of like the S and the R. So if I have a 0, 0, then it's going to store the same value in it that it had in it, whatever it was. If I had last given it a 1 on the output, it'll store that. If the last I gave it was a 0, it'll store that. So if I get 0, 0 on my input, no change. If I get 0, 1, that's like resetting the latch. So I'm forcing a 0 on my output. If I get a 1, 0, that's like setting it. I get a 1 on my output. And again, these could be positive clock edge triggered or negative clock edge triggered. Now, with an SR latch, we have this invalid case. We have a 1, 1 for S and R. And that actually gives us something that's impossible to understand what's happening there. We can't trace what's going to happen when you do that. It just oscillates in a few nanoseconds. However long it takes to process, to iterate through those gates, those signals are going to oscillate very quickly. Now, in a JK flip-flop, we actually use the 1, 1 input case. And what that does is that inverts Q. And so if I had a 1 in there and I give it a 1, 1 signal and the clock rises, I'm going to get a 0 in there. If I had a 0 in there and I get this case, I'm going to get a 1 in there. So it just toggles whatever data happened to be on that input. And so this is the symbol for a JK flip-flop. We've got our J input, our K input, Notice they're very similar to the S and the R inputs. And then we have our clock, which is a dynamic clock. So that means that it looks at the edge, whether positive or negative, in this case a positive edge trigger. And then we have our output Q and Q naught. If we look at this waveform, our clock shows that it's not a very long high clock signal, but again, that doesn't seem to matter for edge triggered circuits, right? We're only looking at the instant right here where it goes from 0 to 1. So at that exact instant, draw a line straight down on the waveform to what your values of J and K are. So if I get a 1, 0, what does my truth table here tell me I need to do? I've got a 1 on my J, and my K is a 0, and I got a rising clock edge. What should the output be? So it should be a 0 here. No, it should be a 1. Sorry. Got my J's and K's mixed up. So we should be getting a 1 on the output there. If we look at the next rising clock edge, I get a 1, 1 on my J and my K. So whatever this value was, it was a 1. We're going to invert that. So now we're going to make that a 0. And then at this clock edge, I'm getting a 1, 0 again. So that's going to give me a 1. And then at this clock edge, I'm going to get a 0, 0. So a 0, 0 will hold whatever value was in there. It doesn't change it at all. So we can do a thing called toggle with a D flip-flop, just like when you have a 1, 1 on your JK, but you have to hardwire it. You take your Q naught and feed it back into your D. And this is actually really useful. And if I go back down here, we use these all the time in circuits. We use them as counters, clock dividers, and timers. So what I've got here is I've got a single clock input, and it goes into one D flip-flop. I take the Q naught and feed it back into the D. So if I were to have a 1 on my D input, that's going to store a 1 on my Q, but that's going to give me 0 on Q naught. And so that sets up that on the next clock rise edge, I get a 0 loaded in here. And then it'll invert again. The next clock edge will be a 1, 0, 1, 0, 1. The thing to note is that the frequency of this output changing is half the frequency of this one. It's half the frequency of the input. So in this case, it takes this thing flashing on and off 2 times to make this flash on and off 1 time. And I've essentially divided the clock by half. If I then take the output of that and put that into the clock input of the next one wired in the same fashion, I get the same thing. So it takes this going off 2 times, on and off, just to get this to go on and off 1 time. And so I've divided the clock by 2 again. I do it again, I divide the clock by 2 again. So it takes this one going on, off, to make this one just go on and off. And similarly back here, that makes this one go on, off, just for this one to go on and off. Now if you notice, if I start from 0, so let me reset everything here. I start from 0, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm counting in binary, with my X9 over here being my most significant bit and my X6 being my least significant bit. And so literally I'm just counting in binary. And so this thing counts up from 0 to 15, and then it adds one more to that, and it just resets them all to 0. So watch that happen here. We've got EF 0. 1, 2, 3, 4, and so forth. But what if I don't want that to go all the way to 15? What if I want to reset it before then? I could just click this button here and reset it whenever I want. But what if I wanted to specifically reset that? I can do that and build useful counters out of that, and I'll show you that in just a moment. So I mentioned this is a clock divider. Well, if I know the clock frequency well enough, and I know how many this is counted up, then I can multiply that together and get the number of seconds that have passed. And so this is not only a clock divider, it's also a timer circuit. And it's also a counter circuit, as we just saw. So the same exact circuit is used in 3 different ways. So now if I show you, this is a circuit in which I've got this counter set up. It's the exact same circuit as above, and the inputs to this BCD to 7-segment display are generated by these inputs here, these outputs of the counter. So if I allow this to count, it should go from 0, 1, 2, 3, 4, 5. It should go all the way up to 9, but this is a BCD to 7-segment display. So after 9, it starts printing gibberish. And the reason is, whenever the designers built this, they put a bunch of don't care values for the outputs for anything above 9. And that ends up giving you gibberish on your outputs. So, it's not very useful here. If I was trying to build a alarm clock with this, it wouldn't work out very well, because most humans can't read what time it is whenever you're going into the hexadecimal numbers, and this thing doesn't even display hexadecimal numbers correctly. So, how might I fix that? Well, we can reset our values here and let me load the simulations for that. So we can reset our values there. So in this top circuit that I'm trying to zoom in on, what I'm doing is I am using these outputs of Q and Q naught for each one of these bits as the counter here that it will create these values. I'm going to take those values into an NAND gate and then take that AND gate output to trigger my reset on my flip-flop. And this reset makes everything in there 0. It doesn't care what was in there before, it forces it to be 0, just as you saw when I clicked the button earlier. But here, what I want to try to get this to do, I want to detect the number 6. So I want to count 0, 1, 2, 3, 4, 5, and then on the number 6, instantaneously, whenever the circuit generates a 6, I want it to reset itself. And so what I do to do that, if I look at my numbers of these outputs, these LEDs here, a 6 is 0, 1, 1, 0. Again, this is our most significant bit. This is our least significant bit. So we'd get 0, 1, 1, 0. In order to get that into an equation, we would say we need x5 naught, x4, x3, and x2 naught. And that gives us the equation for the detector. Now, we've been building detectors all semester. That's whenever we look at a truth table and we try to determine what the min term is for that, that min term detects a certain value of 1s and 0s on our input. And that's the exact same thing we're doing here. So, I'm connecting this one, x2, should be x2 naught because I'm looking for a 0. So I'm going to connect that to my naught output for the Q. This one should be a 1, so I'm connecting that to my D output, or sorry, my Q output. Here, I'm also looking for a 1, so I connect that to my Q output. And then here, I'm looking for a 0, so I'm going to do my Q naught output. And so when this detects 6, it should automatically trigger the reset. Now, I've got a lot of stuff running on my computer, screen capture software and simulation software and all of that stuff. So you're probably going to be able to visibly see the numerical value 6 appear on this 7-segment display for a fraction of a second before it clears it. And in real life, when you build this on a breadboard, you will also see that happen. That's called a glitch. That glitch occurs because I actually have to read the value of 0110. I have to read 6 on my outputs for that to get processed and then reset. And that takes a finite amount of time to do. Maybe it's a couple nanoseconds, but nonetheless, that still takes time to do. So in reality, in the real world, if you built this and you're using, especially if you're using a 100 hertz clock, you wouldn't be able to see it at all. It's never going to happen. If I did a 1 second clock, I still wouldn't be able to see it. The glitch happens so quickly. So let's see. I clicked the simulate button, but my multisim is seeming to go rogue on me. We'll see if it'll actually simulate or if it will crash. It looks like it's crashing. Oh, there we go. So there's a 0, a 1, 2, 3, 4, 5. Now look what this number comes up as, 6. And so for a split second you saw 6, and also 0110 appeared on these outputs. You can watch it again here. And once we detect 0110, that forces this output to be a 1, connects to our resets, which loads zeros into all of our flip-flops here, and we're done. So let's watch it happen once more. There we go. So what if I wanted to do this counting from 0 to 5? Maybe that's my tens of minutes on my clock, right? You go from 00 to 59 on your minutes, and then the next time it increments the hours, right? So let's build a detector that can detect the number 10. So this will go from 0 to 9, and then when it detects the number 1010, it's about to show you, it resets. So again, this is our most significant bit here and least significant bit there. So to detect the number for 10, I'm looking for a 1010. So that is X10, X9 naught, X8, X7 naught. So if I look at my connections for this AND gate, I want to have this connected to the data, or the output Q. That's my 1. This one should be a 0, so that's going to be connected to my Q naught. This one should be a 1, so that's connected to my Q. And finally, this one is Q naught connected to the 0 here. So that will detect a 1010. And this is really useful because now I have something that can count from 0 to 9, and I also have something that's counting from 0 to 6, or 0 to 5 rather, and it resets at 6. So if I want to build something that can count 60 seconds or 60 minutes, all I have to do is connect my tens counter to my 6 counter from above. So I will have, every time I reset this, every time this goes to 1, that will be the input of my 6 counter. So let's see what that looks like. So this counts up 55, 56, 7, 8, 9, back to 0. And so this is my tens counter here. So it counts to 9 and then resets itself. So here we come again. 7, 8, 9, 10, resets it. Every time it resets, that reset gets fed to the input clock of my 6 counter. So this is on 3, 4, 5, and now when it detects 6, 0, 1, 1, 0, it's going to reset itself. And so now this thing counts minutes for me. So I can actually use this to count, well, I could count the number of seconds in a minute or the number of minutes in an hour. And this is one application of a flip-flop. Now you can build this with D flip-flops like I've shown here, or you can build it with JK flip-flops. And so with a JK flip-flop you have a set and a reset value as well that are forcing a 1 or forcing a 0 in here. And note, if there's a bubble on it, that means it's inverse logic, so you have to put a 0 in there to activate or trigger that function. And let's see here. So here is an example of how to build a counter with a flip-flop. So if I have 1, 1 on my flip-flop, it just toggles whatever Q was, it becomes Q naught. Every clock cycle, it'll change over and over again. So if I start with a 1 in here, then the next clock cycle, the rising edge will make that a 0. The next clock cycle will make that a 1. Next clock cycle goes back to 0. And that output goes to the clock of our next flip-flop. Again, I've got a 1, 1 for my J and K, and that builds us another clock here. So another clock divider or counter here. And so you can easily build a counter out of JK flip-flops exactly how I've built that D flip-flop clock we were looking at a minute ago. We can also build things like one-shots, which basically, if I give you a really short input, you will always be able to produce a output of a given time. So whether I give you an input that's really short like this trigger here, or whether the trigger is half as long as the output, or almost as long as the output, or 1 times as long as the output, then this will always give me exactly the same number of nanoseconds between the time that it goes on and the time that it goes off. Now, if I happen to give you a trigger that's longer than that, what happens? There's actually a couple of things that happen. You could have, in certain circuits, your trigger, if it goes 1 for too long, it continuously triggers this. And so it won't actually work as you expect it to. But you can actually design a circuit that you trigger it, and even if your trigger stays high, it still outputs the exact same amount of time before it drops to low. Even if your trigger is still a 1, it's going to ignore it until it goes low and then finds the rising edge again. So those are called, oh, here they go, right here. So in this case, this is re-triggerable. So I can trigger it, and during the time that I've triggered it, if I push it again, it will also give me that same amount of time. Anytime you find the rising clock edge, it gives you that amount of time, no matter what. So that's a re-triggerable one-shot. Here's some more examples of that. Now, we can use a chip called the 555 timer to do that as well. And so that's a very interesting chip. We'll actually build a circuit with this in the lab next week. And we're going to build a circuit that does what's called astable, not monostable. So right now you can configure a 555 timer to do a one-shot or monostable output. You could also set it up to trigger what's called astable, where it continuously goes back and forth just like a clock signal, on, off, on, off, on, off, at a predictable rate of time. And so we can actually design that and build that in lab. The next thing that I wanted to mention was we've already built flip-flops out of SR latches, D latches, and all that. So we've built all the way up to that. We've built counters, timers, and clock dividers, which all happen to be the exact same circuit. What else can we do with latches and flip-flops? Well, with flip-flops, we can actually build bigger memory elements, and they hint at this in our book in this particular chapter. They talk about data storage applications. And so in the next video, we'll go over data storage applications of flip-flops, and you'll be able to see how does memory in a computer work. So hopefully this was enlightening on how we build memory elements for digital logic or with digital logic, and some of the applications that we can use these memory elements for.